All right, our next lesson is on inverse functions. We've dealt a bit with functions now. We've got our quadratic functions, our cubic functions, our hyperbolas, and our square root functions, all the different kinds of functions you've practiced drawing and transforming. Uh, we've got a handle on that. So now we've got to work backwards, do the opposite of what we've just learned, and learn how to do inverse functions. So an inverse function is just basically the opposite of a normal function. What we've got here in our images is we've got a normal function generally drawn in blue, and then an inverse function in red. So you'll learn how to create them algebraically, and then you'll learn how to graph them as well. I can't really think of an example where you'd use an inverse function in real life, but it's a big part of the Year 12 course, so let's get good at it. You might or might not have noticed, but in our title slide, I did refer to the word function an awful lot, and the title of the chapter is actually inverse functions. So it's worth just noting before we get on with the maths that there are some theoretical understandings that we've got to have that we're really worried about whether something is a function or not, and whether the inverse that we're about to make, this opposite rule we're about to make, is a function as well. So I've just put a few little notes here to show what we're going to be doing, and there's just a few things worth highlighting for you guys before we start. So we're going to be working with functions mainly, and we'll get into definitions of what is and isn't a function, remind you of that soon. But basically, we only have an inverse function if the inverse of our function is a function. So it's got to pass some of the tests that we've talked about in previous lessons that I'll show you again, but you'll see the function notation pops up in our work. So the right way to name a function is call it f of x. And if we have an inverse function, we'll be writing it as f to the minus 1 of x. This is formally how you write down a function and an inverse function. So we're going to be using the letter y because the letter y is much easier to do algebra with than like f of x. Like I know how to times y by 2, easier than I know how to times f of x by 2. So just a note that when we do our algebraic fiddling and our algebraic rearranging, we'll use our variables x and y rather than like f of x and x. But if our inverse is a function, we'll have to write it using proper function notation. So we'll be using our f of x and our f to the minus 1 of x. So if we're dealing with functions, we use this and we use that, but we can use x and y to do the algebra. So what an inverse function actually does, or an inverse relation does if it's not a function, is pretty simple. It takes all of your coordinates, your ordered pairs, your x's and y's, and it swaps them around. It puts them around the other way. So all your x's turn into y's, and all your y's into x's. So your coordinates, which formerly went x and y, now go y and x instead. So if you just get a set of ordered pairs as a function rather than a rule, it's pretty easy to just write them in reverse. So the coordinates on our inverse function or our inverse rule, we'd have 10, 1 as our first point, 20, 2 as our second point, and 30, 3 is our third point. Now, most questions won't involve coordinates, they'll involve the actual rules. But what the rules are going to do, and the reason why we're doing the maths that we're doing, is we need to make sure all our x's turn into y's and all our y's turn into x's, and then you've got an inverse opposite function. And I'm going to stress again, because this theoretical understanding is really, really important, that starting with a function doesn't mean that you'll have an inverse that is a function as well. So not every function in the world will have an inverse function. Okay, everything has an inverse rule, everything has an inverse relation. We can make an opposite out of anything, but not all of those inverses or opposites that we do will actually be a function. So once we get to this algebra and once we rearrange our function, we've got to check that the new algebra thing we've made is a function. Okay, so we've got to check whether things are functions or not. And let's have a look at what defines a function and what doesn't. Let's remember that. So in a lesson in term one a little while ago, we did learn the definition of what is and isn't a function, but I've got a nice little glossary page for you if you want help with that. The main way we had of proving whether something was a function or not was passing the vertical line test, which means that we can just, on our graph, draw a vertical line at any point whatsoever, and that vertical line is only allowed to hit our graph once. So if I'm dealing with just a linear function, a really basic one, it doesn't matter where I draw my vertical line, I only ever contact my graph or run into it once. Okay, this is called one-to-one correspondence. And the reason why this is one-to-one correspondence is this graph actually passes a horizontal line test, which we've never talked about before. But this is going to come in handy today. Okay, so a graph like this passes both tests. It's got a one-to-one correspondence because I can only hit it once going this way, and I can only hit it once going that way. Well, all you've got to remember is these green lines here. As long as my green line hits my graph once, it's a function. So this here is a function as well. I can classify it as a function. Okay, so everything on the left-hand side of this red line I've put here is a function. These two graphs are functions because it doesn't matter where I draw this green line. It only hits my graph once in one spot. This one fails the second test, which is my horizontal line test, because this blue line I just drew here actually hit this graph 3 times, not just one, which means it's got a many-to-one correspondence. Okay, but a one-to-one correspondence and a many-to-one correspondence, they're still all functions because it's all about that vertical line test. What we've got over here on this side is we've got two graphs that are going to fail this vertical line test, which means they're not functions, right? All of those lines are hitting my graph more than once, right? This one hits the graph twice. This one hits the graph twice. As soon as there's one line, one vertical line I can draw that hits my graph more than once, it's not a function. But these are classified differently. This one is a one-to-many correspondence. This one's a many-to-many correspondence because this one passes this test. This one fails this test. This one hits it once. This one hits it twice. But it's all about the green lines. If I want to know whether something's a function or not, then it's got to pass that up and down test. Now, the reason why I'm drawing this horizontal line test is the only functions that have inverse functions are these ones here with a one-to-one correspondence, right? So a graph has to pass the up and down test to be a function, right? So this is a function, that's a function, but it has to pass the horizontal line test to have an inverse that is a function. So this would have an inverse function, this one wouldn't have an inverse function. Okay, so try drawing horizontal lines to see if there's an inverse function. And that's once you've drawn your vertical lines to prove whether your original graph is a function or not. So that's probably enough theory for the moment. We should probably actually do some worked examples. So what we've got here are 3 functions, f of x, g of x, h of x. We've got to determine which ones are one-to-one and have inverse functions, because only graphs that are one-to-one will have those inverse functions. So we can make an inverse out of any of these. These all have inverses, but I think we'll find only one of these will have an inverse function. Okay, so let's just sketch them. So these should be kind of types of graphs or functions that you are familiar with at this point. We've got a cubic, quartic, and this is a hyperbola with a couple of transformations that's been done to it. So let's just briefly sketch them. So a cubic goes across and up, kind of smooth. This point here is up a bit too much, so let's just try and smooth that out. It's really important to get those graphs looking like actual graphs. That'll do. A quartic is a cubic but steeper. And hyperbolas, well, we know we've got to draw the asymptotes first. So this plus 2 means that there is going to be a shift this way, 2 units, which means we can kind of just draw an asymptote here. This isn't me doing a vertical line test, right? This is different, a different dotted line than before. It's just an asymptote. This one moves it up 5. So we'll just put it around about here. There's a negative in front of my hyperbola, which means it's upside down. So normally the hyperbola would be in this quadrant and this quadrant, but it's going to be in this quadrant and in that quadrant. Okay, so what we've got to do now is just see if our graph passes these vertical and horizontal line tests to see if they're one-to-one or not. Okay, so you ask yourself the question, is there any place on this graph, say on this first graph, where I can draw a horizontal line and hit my graph twice? And there really isn't. Any line I draw will hit this graph once, and the same thing goes for this test as well. So this graph's going to pass both tests. Just a cubic like this will pass both tests. Cubics are nice like that. So the type of correspondence this one has, this is 1-to-1, and it has an inverse function. So when we actually make the inverse, it would be a function as well. Okay, so this graph, this quartic, is a function as well. As I can't draw a line like this and hit it twice, but anytime I draw a dotted line across kind of this part of my graph, hit my graph twice, which means it's not 1-to-1, it's many to one. So there's no inverse function. We can create an inverse, we can make an inverse graph out of it, we can make an inverse relation, but the inverse of this graph wouldn't be a function, and you'll see why later on. So this graph here, I've got my asymptotes, they're not my vertical line tests, so I'll use a different color, we'll go back to purple. I can't draw a line that hits this graph twice, going that way, and I can't really find a spot where I'd hit my graph twice, going sideways. Right there hits it once, this only hits it once, this only hits it once. So I guess we could say that this one is 1-to-1 and has an inverse function too. All right, now we can get up to the fun part, which is doing the algebra involved in building an inverse. That's why we're all here, right, to do algebra. So I've just given you a few quick steps to follow to make an inverse, and then you have to check whether it's a function. We can't assume that anything we make is going to be a function because some things make inverse functions and some don't. But these are the steps involved to get to the end result of an inverse function. So the first thing we want to do, because we're working with algebra, we don't want to work with f of x. It's ungainly to work with f of x. When we're working algebraically, it's hard to do things to f of x. It's really easy to do things to the letter y. So the first thing we're going to do is we're just going to let f of x equal y and work with something that we're more familiar with seeing, which is something like this: y equals 8x cubed take 4. So I've just rewritten it so it's got y instead of f of x. Hopefully the next 3 steps are that easy as well. All right, we're a quarter of the way there. So step 2 is just swap x and y. Since our inverses generally just swap our x and y coordinates over with each other, why don't we just swap our letter x and our letter y with each other as well? Yeah, so we're going to rewrite it as this, right? This is step 2. I'm literally just swapping where x and y are there, the old switcheroo. All of our rules or our functions always have y at the start though. So once we do this, we don't have a nice equation anymore. So step 3 is the big one. So I've done step 1, I've done step 2. Now step 3 is I now need to transpose my equation, which means rearrange it to make y the subject again. Okay, we've got an equation where x is by itself. We never have those. We like to have y by itself. So we're going to work backwards and rearrange everything until y is the letter by itself, not x. So show our working out for this one, right? Working backwards, doing the same thing to both sides. I'm going to plus 4 to both sides of this equation, right? I want to just cancel down this side till y is the only thing left there. So we're going to cross that 4 out. There's going to be a plus 4 over here. So on this side, we're going to have x plus 4. And on the other side, we've got 8 lots of y cubed. I've got 2 more steps to go because you can see there are 2 other things being done to y. The next thing we've got to get rid of is the 8. We don't want that 8 there. We're going to move the 8 to the other side. So our working backwards step is to divide both sides by 8. The purpose of doing that is to cross it on this side. Right, it's not going to be there anymore. So let's write what we've got left over. We'll move it up here. So the simplest way to show that I've divided this side by 8 is to put it on top of 8. There we go. And on this side, I've got y cubed. So I'm pretty close to getting y by itself. I've just got this cubed. I don't want that cubed there. So we've learned at this point, right, that the opposite of cubing is to cube root. Right, so I'm gonna put that there. And the whole point of doing a cube root, remember, is to get rid of that cube there. Right, it's going to cancel that out. It's going to cancel that out. Right, the cubed and the cube root cancel out until we've just got y by itself. So I'm really just going to do it on this side as well. So at this point, I might just swap what side we're working with because I want to have y on the left-hand side. It's just nicer. It's neater to have y by itself over here. So y is going to be equal to a big cube root. And underneath that cube root, we've got x plus 4 on top of 8. Okay, now we started with a pretty basic cubic, and we saw in the last example that pretty basic cubics are one-to-one, which means they have inverse functions. That probably means that this is going to have an inverse function as well. I'm now worried about question B and whether I can do step 4, because this step here was the completion of step 3. If the inverse is a function, we've got to write it using function notation. So cube roots don't have two answers in the same way that square roots do. If we had a square root here, we might be in trouble. But cube roots are nice. It's going to make it a function for us. So we're now going to just answer B by rewriting the relation in function notation. We're going to call it the f minus 1 of x. This is how we denote we've found an inverse, the power of minus 1. And we're just restating our rule. So it's a big cube root, x plus 4 on top of 8. So we've turned our original rule into its inverse. Okay, we started with a cubic. We've ended up with something that's a cube root, which probably makes sense if we're doing the opposite. Cubics and cube roots are generally pretty good at being one-to-one, which means that this inverse is a function, and I've written it as a function. So is the inverse a function? Yep, sure is. Unfortunately for you guys, the algebra isn't the end of it. Once we've done the algebra and we've made our rules, we've also got to be able to graph them. We've also got to be able to graph them without having a rule, without being able to look at that and cheat. So you're going to have to learn how to sketch a graph of your inverse function as well. So step 1 is to actually have a graph in front of you. You can't sketch an inverse unless you've got the graph on the paper to work with. What you'll be then doing is creating a line of symmetry because they're just opposites of each other. So there's going to be just a mirror line. They're going to just be reflected in a line, but they're not reflected in the x-axis. They're not reflected in the y-axis. They're going to be reflected in a line that has the rule that x equals y, which is a line that goes really nicely through. Here we go. That's the button I'm looking for. It just goes through here. Okay, so that's going to be your mirror line. That's going to be where you're looking to reflect it across. Okay, so it's not in this axis, it's not in that axis. You're going to be reflecting anything that's on this side of this green line, which is kind of like it goes through the coordinates 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. You just try and draw it as, you know, halfway through as you can, halfway through this right angle that is your quadrant here. And then you're going to reflect it to the other side. So this is our line of symmetry, and then you've just got to be really, really careful and try and make a nice sketch. So let's have a go at that together. All right, so what we've got on the screen here is a pretty funky looking graph. We've been asked to do two things with this function, f of x. They want us to sketch the graph of the inverse. So we're going to have a go at sketching that in a minute. And then they want us to answer the question, is the inverse a function? I think with what you've been taught so far this lesson, it's really worth knowing what you're getting into before you start. So you really should be able to answer question B before you sketch the function. What you'll note is that this is a function because anytime I draw the dotted lines through this graph, it only ever hits it once. But what you should note is there is a point here where if I draw a horizontal line through my graph, that it contacts the graph more than once. It contacts it 3 times, which means it's not a one-to-one correspondence. And because it's not one-to-one, it's not going to have an inverse function. So let's just flat out say right now, it's not an inverse function. We shouldn't have to worry about that. Okay, now the actual act of sketching this graph, we've done step 1 from the previous slide. We've got a graph in front of us. I can see it on the screen. What we've got to do now is we've got to create our mirror line, our symmetry line. So you kind of just got to go through there and give it a bit of a 45-degree angle kind of feel between here and here. Once you've got your mirror line, you'll be able to sketch by using this as your line of symmetry. What some people like doing when they've got their inverses on a piece of paper is they just draw that mirror line, then they do fold the paper over to have a look at it. A bit like making a butterfly when you're in kindergarten. You paint one side, you fold it over, you've got a symmetrical butterfly now. You could almost do that if you draw enough ink. Like if you just went over this graph with really, really, really like wet ink, like you've got your broken pen or something, and you fold it over. When you unfold it, the inverse should be on the screen on your piece of paper if you do that. That's cheating, so don't do that. Let's actually try and draw it. The easiest way, I think, to approach an inverse, because it's a bit of a nebulous theoretical skill that some people who are really good at algebra just can't do, because it's a bit more like visual. I think it's good to start with where your graph intersects this green line that I've drawn. So you'll have to draw that mirror line. You can't do it without a mirror line. And then your graph at some point is probably going to touch it. If not, then just try and find a reference point like an endpoint or an asymptote or something to focus on. But you've really just got to make sure your graph is the same distance on this side as it is on that side. So what you'll see is this part here touches my green line, then it kind of moves out this way. So if I mirror that on the other side, I kind of start here and I move out around there. And then from this point here, it shoots away from my green line like that. So I want to make sure I move away from my green line in this direction as well, right, as far as I need to go. Okay, so I've mirrored this part of my graph so far. Now I'll focus on doing it on this side. So this part here kind of just bends slightly away, kind of trying to make that kind of shape there. Goes a bit like that. And then it kind of moves kind of backwards and away from my green line. So I'm going to do the same thing. I'm going to move backwards away like this. And that's basically sketching an inverse graph. It's imprecise, right? You're all going to be slightly different and slightly off. If it looks like you know what you're doing, then you'll get the marks for doing this. And if we do want to prove now that it's not an inverse function that we've sketched, you can see if I draw a dotted line through this part here, it hits the graph more than once. Okay, so we've got that reaffirmation that this inverse is not a function. All right, so for our last worked example, we're just going to put it all together. We've got a rule, a square root rule that we're going to work with. We're going to find the rule of the inverse, and then we're going to just put it all together, and we're actually going to sketch the graph, sketch its inverse, and then we're going to do the domain and range of the function and its inverse and learn something about that too. So first things first, let's find the rule for this inverse. So step one is to make sure we've got letter y to work with. They haven't written this function in function notation using f of x, so we've already got y there. Step two, let's swap x and y over. So let's put x over here. Let's put y underneath the square root. The -2 is under the square root, the +1 isn't, right? Really important to note that. And we'll start rearranging and sending stuff to the other side as best we can. So the easiest thing to send to the other side is this +1 first. So we've got x plus 1 on this side. We've got root y, take 2 on this side. The next thing to do to get y by itself is to get rid of the square root. So we want that square root gone. The opposite of square rooting is squaring. Right, so we've got to square this side, and we've got to square this side. Right, the whole point of squaring on this side is to just remove the square root from on top of that. That's going to cancel out with that, but there's going to be a squared on this side now. So what that looks like, the x plus 1 should be in brackets because this entire side of the equation had to be squared. So by putting it in brackets, putting that there, the whole thing gets squared. On the other side, I've got y minus 2. So our last thing to do is get rid of that -2 by plussing 2 to both sides. And at this point, I'm going to get y across the other side. And I'm going to put x on this side. X plus 1 squared. And the +2 is there as well. So I have found the rule for the inverse. It's a nice looking quadratic with a turning point at -1, 2. But there it is. There's our inverse rule. All right, so we're almost there. Our next goal is to sketch the graph of the function and its inverse. So I've just put the rules for them here. We've got our square root graph, we've got our quadratic graph, and we've got to sketch them both on the same set of axes. So we'll start by sketching the original graph, the square root graph. That's important. I'll use black since it's the color of the text. So we know that square root graphs are gun-shaped, right? They just hook. They hook around from the endpoint. So we should know by looking at this, because we've learnt our transformations, that that -2 sends it that way 2, or 2 units to the right, and it shifts 2 units up. So we've really got an endpoint that's about here, we'll say, and then it just travels off like that, and that's our square root graph. The next thing we're going to need to have, if we're going to sketch the inverse, is we're going to need our line of symmetry, or our mirror line. So we'll just put that through here. And then we just have to make sure this is mirrored over here. So what you might notice, we're not going to be drawing our entire quadratic. If I was just going to sketch this rule, this full rule here, it would be a U shape. But because this rule is responding to this rule, and it's the opposite of this rule, it's going to have a restricted domain. So it's not going to go forever. It's only going to go wherever this exists, but kind of the opposite of it. And we'll see how that works when we answer part D down here, when we state the domain and range. And you'll see it's really easy to know the domain and range of an inverse, as long as you know the domain and range of the original graph. So really all we've got to do is think about the endpoint. So if this original graph had an endpoint that was across 2 and up 1, then that coordinate's going to swap. For the inverse, it's going to be across 1 and up 2, right? So 2, 1 turns into 1, 2. And then it kind of hooks along here. So we kind of need to just hook and go away from it that way. And we've got something that looks pretty symmetrical, so you'll probably get your mark if it looks pretty symmetrical and you're on the money. So now when we're stating the domain and range of the function and its inverse, let's just focus on the function. Let's focus on this one. So the domain of this particular graph, that's our x values, that's where my graph exists. It's all about the endpoint, right? This graph starts at 2. Okay, so that 2 is part of the graph. So it starts at 2, and it goes all the way to infinity. And then the range, well, we can probably have a look at the endpoint as well. The range is all about knowing where your graph exists from bottom to top. So the lowest point on our graph is 1, right? We've got that from our endpoint, from our transformation. It starts at 1 and it goes all the way up, right? Very, very slowly up, but it goes all the way up. So the range is 1 to infinity. Okay, so we could now look really closely at this graph and try and figure out its domain and range, but here's how you do it. The domain and the range of your inverse function are the range and domain of your original function. So you're really just swapping the range from the first one to the domain of the second one, and vice versa. So if I know the range was from 1 to infinity in my original function, then the domain of my inverse function goes from 1 to infinity. So these two are just flipped when we're finding the domain and range of the inverse. All right, so nothing too much to worry about there for you guys, as long as you can tell me the domain and range of your original graph. So then the range is just the domain of the original one. So it starts at 2 and goes to infinity. Okay, from 2 up. And that's it for that example. Okay, so that's everything that we need to know about inverses, their functions and their graphs. And it should be enough to get you through most of this chapter. Hopefully we'll be working through this chapter together, whether it's online or in person in class. But by watching the video, you'll have kind of that understanding of the theory behind inverse functions, whether things are functions or not, how to algebra them and how to graph them. It's an important chapter, if for no other reason than it's a big part of Year 12, and there are always questions on the exam around it. So we want to get this right and kind of have it embedded. So we want to try to do the whole chapter if we can. The preps, they're all really important. They're all really doable, using just the worked examples and the stuff that you've just heard. So make sure you have a go at them and try and get them right. The pracs are a bit tougher. They're a bit more theoretical. But but I'm going to, in a second, go over some of the theory around them in case you want to have a good go at them. So if you want to ignore them and go do some work now, you can. Otherwise, stay tuned for this example. Okay, so what I've got on the screen here, it's question 6 from the prac section of this chapter. It's the last question in the chapter. One of the harder ones in there, I guess, just because of the notation and the stuff that they're talking about here. So they've given us a function, f of x, and if you have a good close look at it, you should recognize it as a quadratic because we've got x and it's squared. And we know that quadratics are U-shaped. Now, they're asking us, when will this function have an inverse function? Okay, so if we go back to our earlier slides over here, with all this scribble on it, what you might remember from what you were shown. See if I can get rid of these. The only types of functions that have inverse functions are these one-to-one correspondences like this. Okay, so it has to pass the vertical line test and the horizontal line test as well for it to have an inverse function, right? So none of these here would have inverse functions because they fail that horizontal line test. Okay, so that's the problem with a quadratic, and that's why in Methods Year 12 they love asking these questions about quadratics, because a quadratic is inherently U-shaped. So any quadratic fails this test here. So what they're really asking you to do here is they're asking you to restrict your quadratic, only draw part of it, so you can actually have an inverse function. Okay, so they want to know, where does the inverse function exist? So these questions are always really just questions of turning point, because if I think about drawing a quadratic, as I draw it here, this thing I'm drawing has an inverse function because it doesn't turn around and fail that red line test. Okay, so as soon as I get here to the turning point, right, this is my turning point here, I've still got an inverse function because it passes that test and it passes that test as well. But the moment I turn around and start going back up, now I fail that test, I won't have an inverse function. So they're really just asking, where should I stop to have an inverse function? So if you can look at this equation here and figure out where the turning point is, and then you can restrict your domain going side to side, one of the answers will be in here and you'll get it right. So good luck with that.